Yeah, after spending so much time on creating arrays and indexing individual values in an array, let us finally get to a more interesting topic and talk about NumPy array math and universal functions. Universal functions, that's actually not too long, but programmers like to abbreviate things. So in NumPy it's called ufunc. So ufunc is a short form of universal function. And a universal function is a really cool concept because it makes working with NumPy arrays way more efficient and convenient. And that is by enabling a concept called vectorization. So vectorization means that we are calling an operation, a mathematical or arithmetic operation, on sequence-like objects. So, for example, think of it like this. We have one operation that we want to execute on all values in an array. And let's say this operation is just mathematical addition. We want to add a number to every element in an array. So if I want to add the first value to the array, I can call an addition function in my program. And if I want to add again the same number to the second value, I can do the same thing. However, if I want to add the number to the second value, I don't have to really wait until the first addition on the first number finishes. I can actually do that at the same time, like computing that in parallel, because there's no dependency between the elements in the array. So in that way, it would be wasteful to use a Python for loop to add these numbers to the array. There's a way called vectorization, where we can actually call the same operation in parallel on the whole vector or array. And I will show you how that works in NumPy. It's actually pretty intuitive, but I thought it's kind of useful to talk about it so you kind of get an idea what's happening under the hood in NumPy when you're calling certain functions. So also, after watching this video, I highly recommend you to check out the official documentation for the complete list of all the ufuncs implemented in NumPy, because there are more than 60 ufuncs right now. And we will not talk about all of them. Actually, we will maybe only talk about a handful of them. But it might be useful for you later to scroll through this list and see what's available. And you may need that in a future project, for example. Of course, you don't have to memorize any of that. It's more about like just seeing what's out there, and then maybe in a future project you think, okay, I may have to compute, I don't know, the arc10, for example, and then you know, okay, this actually exists in NumPy, so I can use this ufunc here. Anyways, so let's get back to some examples here. Actually, to give you an example of ufuncs in NumPy, I thought it's maybe easiest to talk about element-wise addition. So consider this hypothetical weird scenario that we have right now, where we have a list of lists or a two-dimensional array. Say this is our 2D array implemented in just Python. It's a list of lists. If we wanted to add the number 1 to each element, so if we wanted to add 1 to each element and the array already exists, how do we do that? So how we can do that is by using for loops, right? It's actually the only way we can do that. I mean, there may be other ways, but this is like the natural way we would do that in Python. So we would iterate first over the lists in this list of lists, and then iterate over each element in the list, and then add the number 1 to it. So we would have actually 2 for loops. And let's just check if this works. Okay, this seems to work. Actually, I just see I had executed this notebook before. Let's do it like this, so we can't see the results before we talk about it. Okay, so you can see it successfully incremented each value by 1. So before we had 1, 2, 3, now we have 2, 3, 4, and so forth. However, if you recall from the KNN lecture, this is a very, very inefficient way of incrementing each value by 1, because we have 2 for loops, which means we have a big O of n squared, right? So this is super inefficient. And if you may ask, okay, can't we just do this more efficiently? Can't we just do LST plus 1? Does that one work? No, unfortunately in Python this would throw an error. So I think there is no much more efficient way than using this for loop approach. Of course, we can use list comprehensions, and you may notice in future notebooks, and I think also already in the KNN notebook I shared last week, that I'm a big fan of list comprehensions in Python. And by the way, I also should note, list comprehensions are, I would say, a little bit weird. It's just writing this thing here in a more compact form, so you don't really have to use them. You can also just use regular Python for loops. I don't know, for some reason they were newly introduced back then, maybe half a decade ago or something like that, and I'm always like, there's a new function in Python, I'm really excited to use that, and then I just started using that very extensively. Sometimes I just use list comprehensions because I like them, but I realize they can be confusing, so I may actually should use more for loops. And also, if you see list comprehensions that don't make sense, just let me know on Piazza or something, and I am happy to explain it to you just using regular for loops. In any case, so this list comprehension would actually do the same thing as these two nested for loops. So this would be slightly more efficient. You can maybe time this via the timeit command and see that this is maybe a little bit more efficient, but not by much. And you can see it's doing the same thing. However, it's not, so the reason why it's not that much more efficient is that we still have two for loops here, right? So it's kind of a little improvement, but still two for loops. It's big O of n squared. So it's still a very inefficient approach doing that. So an inefficient approach might be using ufuncs. Ufuncs would do the vectorization that I talked about earlier at the start of this video. So vectorization means that we can compute the addition of this element, of the element 1, at the same time on each value. And in NumPy, certain functions are supporting this way, the ufunc, the universal function operation, and one of them is numpy.add. So numpy.add would add the number 1 to this array. And to be precise, this would be called a binary ufunc. So let me write this here, binary ufunc. And the reason why it's called binary ufunc is because this function takes two arguments, and binary, two values, like this is just like a way of calling this a binary ufunc. There are ufuncs that are unary, so there's only one thing that goes into this here. For example, if you think of exponentiation, if you compute the power of an element, it's just one, or let's say just a square root. Square root would be a unary. This would be a unary function because we only have one value. A binary is if we have two arguments here. Any case, let's not just get distracted by the terms binary and unary here. So here, this is the addition operation in NumPy, and it will add the value 1 to the whole array. So it will do that at the same time. So it doesn't have to doesn't have to be a for loop basically. So let's call it. And again, you can try the timeit function. You will find that this is way much faster than using the for loops in Python. And also know that there's a concept called operator overloading. Here, operator overloading. So what that means is that certain symbols on our keyboard or in the code, certain symbols like plus, minus, division, multiplication, power of, and stuff like that, are overloaded. That means if I have two, let's say, Python integers like 1 or 1 plus 2, then this will perform Python addition. However, if the left side here is an array, this will perform the NumPy addition. So under the hood, this will actually do the NumPy addition here. So in that way, this is called an operator overloading because we don't really have to call numpy.add. We don't have to do this. Oops. This, we can just call it like this, and it will automatically use numpy.add under the hood. I don't have a good example now of like showing it to you. You would have to dig into the source code to see that this is actually the case, and which would probably take me 5 or 10 minutes now to go to the NumPy source code. But I can maybe, if you are really interested in that, just post on Piazza. I can just show you the source code in NumPy that is doing this operator overloading, if you don't trust me that this is actually doing numpy.add. Okay, so yeah, here I have the numpy.add. Yeah, another common one would be computing the power, so raising each element to the power of 2. So squaring each element. So it's another ufunc, and this would be a unary ufunc. Yeah, and like I said, there are many ufuncs implemented in NumPy. If you go back to the website at the top that I showed you, you can check the whole list of ufuncs. Now let's get to a more interesting case of a ufunc that is involving the reduce method. So the reduce operation, what it does, it's applying an operation along an axis. So by default, it applies it to the first axis, axis 0. And I just introduced to you the numpy.add function. So if we combine it with this reduce here, oops, I moved it around. If we combine it with this reduce here, what will happen is it will compute the column sums. So if we have an array, let's step one step back and just call, oh no, it's actually fine. Sorry. So let's consider this example. So we are computing the column sums. So what happens here is we will roll over the first axis, which is the axis 0. So what it means that it will use the add function like this. It will roll over, thanks to this reduce here, over this axis. It's hard to do it with my mouse, but it will roll over 1 and 4, add these two numbers, and then reduce them to one number. So the term reduce is maybe a little bit weird, but you can think of it as combining numbers, multiple numbers, into one single number. We can actually do that also for an arbitrary number of values. Let's do 578 here. This should, or 579. This should also work. So it will still roll over these axes, basically. So reduce is combining two values or more than two values, everything that is contained in this axis. So in this axis, we are talking about the 0 axis. It's rolling. So what I mean is rolling over the first axis, axis 0. So it's rolling over this and then combining these elements. So if we wanted to compute the column sums, we can do this. And similarly, we can roll over the second axis. So we can do 1, 2, 3. This would be 6, right? And so we would have 1 plus 2 plus 3. We would then squish them, so reduce them to one single number. This would be 6. And 4, 5, 6. This is 9 plus 6, it should be 15. So that would be 6 and 15 if we execute that one. So yeah, so the reduce function, it will tell us over which axis we want to do a certain operation. However, this is kind of unnecessarily verbose. I'm just explaining the concept behind the reduce. And you maybe have heard about the term MapReduce or Hadoop. Hadoop is actually an open source implementation of MapReduce, which is a concept that was developed at Google. And the MapReduce algorithm, it's kind of mapping an operation to multiple compute nodes. And then there is at the end one compute node that combines the results that the other compute nodes computed, basically. So yeah, that is maybe a lot, but you can think of it like this. So you can think of it like you send the operation 1 plus 4 to compute to the computation node or compute node number 1, and the operation 2 plus 5 to the compute node 2, and then the operation 3.6 to the compute node number 3. And yeah, and these will be then reduced to the individual values. So this will be reduced to the 5, 7, and 9. So in that way, we do certain things in parallel. We don't have to wait until 1 plus 4 is finished until we compute 2.5 and 3.6. 3 plus 6, and so forth. And yeah, and that is one advantage of the ufunc. We don't have to wait until this computation finishes before we compute this value. Of course, we are not having a compute node when we compute things in NumPy because it's all operating our computer. However, there's another library called Dask. It kind of supports the NumPy API also, and this is capable of scaling up computations across multiple computers. Okay. Yeah, of course, we can do things more conveniently, so we don't always have to call add.reduce, which can kind of become verbose. And like I said, programmers don't like verbosity, so there's of course a convenience function. It's just called the sum. So it's actually doing exactly what we've done above. So we can call this one to compute the column sums. This is equivalent to our first case here. So this case. So we didn't write x is 0, but it does the x is 0 by default. So this would be equivalent. The reason why I'm mentioning this is if we don't provide an axis argument, it will compute the sum of the whole array. Anyway, so this will do the same as add reduce with no argument, with a default argument x is 0. And like I said, it's rolling over the axis. So it's like rolling over this axis, the x is 0, the rows, and then compute these values. And here again, it's going with x is equals 1 over the columns. So yeah, like I said, this would compute the sum of the whole array. So if we wanted to compute the row sum, we would do this. Yeah, and like I mentioned before, there are many other ufuncs out there. Here I listed some of the most relevant ones, I think. So these are the ones we will be probably using a lot in this class, so it might be useful to go over these and what they are. Yeah, I'm just looking through these. I think maybe one word of caution regarding standard deviation and variance here is that these will compute the population variance in standard deviation, not the sample variance in standard deviation. Yeah, as a statistics student, this may be a little bit confusing, probably because most tools out there compute the sample variance by default. So what I mean is this doesn't compute or include Bessel's correction term. So let's maybe take the standard deviation as an example to show you what I mean. So if we have the standard deviation, let me write this down, square root, right? It's a fraction here, 1n. Yeah, live writing and coding while speaking is not really my strength. Am I forgetting something? I think this should be squared, right? Let me check. Looks good, right? So yeah, this should be the standard deviation, the regular one, the population one. And let's maybe code one example. I don't know, some fantasy values here, 1, 2, 3, 4, and see in NumPy what that results to. It should be okay, 1.11. Now let's just to see what's going on, implement this ourselves. Let's take this function here. So what we have is we have to compute the mean first, right? So the mean would be sum for every value. So here I'm using a list comprehension. I for I in I call it a, and then yeah, this should be my mean. Oh, divided by the length by n. So maybe to make that more clear, this is n, so we can write it like this. And now let's compute the values. Yeah, sorry, I have to maybe stop talking for a second because I can't really talk while I'm writing. Yeah, square root is in Python, or you can also write it, or in general is over 1/2, right? What am I forgetting here? sum over, oops, something's weird here. All right, this is it, I think, over n. All right, yeah, there we go. So this gives us the same result, and yeah, we can see that we didn't have Bessel's correction here. If we wanted to have Bessel's correction, I have to do a -1 here, right? So this would be Bessel's correction. And in NumPy, there's a parameter called degrees of freedom, or sorry, delta degrees of freedom. So it would be DDOF. And by default, it's set to 0, so no delta degrees of freedom. And here, delta degrees of freedom would be the delta. So the delta means difference. So we have a difference of 1, right? So because we have n-1, we have n-1 degrees of freedom. So this basically stands for the -1 here. So this would give us Bessel's correction term. Yeah, it was just like a kind of little tangent here. I just wanted to explain to you that this variance and standard deviation in NumPy won't by default use the sample variance. And by the way, in machine learning, it doesn't matter anyway. The only cases where we are using standard deviation variance is for normalizing or standardizing variables. And there it really doesn't matter whether it's Bessel's correction included or not, and so forth. Sort, arcsort and stuff, arcmin, arcmax. I think we will discuss that later, but maybe if you are curious, sort is just sorting an array of values. So if we have an array, let's say NumPy array 5, 7, 1, 3, something like that, we call numpy.sort a. This will give us the sorted array, and arcsort will give us the indices that we can use to sort the array. So it will give us the index position. So this would be index position 0, 1, 2, and 3, and it will then be 1, and this would be 3, right? This would be 0, and this would be 1. Sorry, this should have been 2. Okay, 2, 3, 0, 1. NumPy arc sort. So this gives us basically the 2, 3, 0, 1. The sorting order of the indices. So I can actually use that one to sort my array if I wanted to. So this is actually useful if we want to shuffle two arrays in unison and stuff like that. I think I showed you how to shuffle an array in unison using that approach in the KNN lecture, but I kind of forgot what I exactly did there. It's kind of a week ago, and yeah, I think that's at least how I would do it. If I would sort two arrays in unison, I would use the arcsort. And then similarly, numpy.max and arcmax behave similarly. So max would be for finding the highest value in an array. So here, for example, this would return 6. And if I do an arcmax, numpy.arcmax, it will give me the index position of the highest value. So it will be 0, 1. This should be returning a 1. And then I could get the highest value if I wanted to by doing a numpy.arcmax a, or I can just save that as index and then do it like this. It's usually useful if you have two arrays or more, two arrays or more, and you want to look up, or they belong together, and you want to look up the highest value or the value corresponding to the highest value in another array. Just spontaneously, one case that comes to mind is eigenvalues. If you do an eigen decomposition and you want to find in an array of eigenvectors the eigenvector that corresponds to the highest eigenvalue, so you can use NumPy arcmax to find the highest eigenvalue in the eigenvalue array, and then you can use that index to look up the highest eigenvector in the corresponding eigenvector array, and so forth. But yeah, these are I'm rambling on here. I noticed I should maybe stop this video, because we will have another video about NumPy broadcasting, because yeah, this will be another very important topic. This is actually one of the, I would say, most fundamental topics in NumPy. One of the cool, it's jumping around here. One of the cool features in NumPy, which will allow us to do certain things way more efficiently. And this can also cause some confusion in the context of linear algebra. So, but yeah, I don't want to take away of this right now. We will cover this in the next video.